Hello everyone, thanks for joining us for this follow-up webinar from our ViaGrade virtual conference. I am Mathieu. I will be your host today along with Mark that will help me on this presentation and on the final Q&A at the end of the presentation. So how it will work, everybody should be on mute and please stay on mute during all the presentation. I will do a few slides and few explanations, and you have a chat window in the WebEx application where you can put your questions during the presentation. We will collect them and we will answer all of them at the end of the presentation. Thank you. So let's start this webinar about what is ViaGrade unique architecture. So you have maybe attended also our previous webinars. So the first one was about our complete workflow solution from offline simulation through driving simulator up to in-vehicle testing. Now today we will focus on how our driving simulator architecture is unique and what it gives as advantages like unparalleled separation of chassis and body behavior. And last week you have been able to witness the open environment webinar that describe how our turnkey solution can be adjusted to customer needs. All the two previous webinars, complete and open, are available on our ViaGrade YouTube page, and the Unix architecture webinar from today will be also available in a few days. So let's jump into it. So a quick introduction about our quest as ViaGrade. Let's say that until now, the standard way of developing new products was to dream it, to have CAD designing and prototype designing virtually, then to make a physical prototype, to try it, and to reloop on this prototype to refine the solution. Now we have a new paradigm in the automotive industry where we want more than ever try our solution and investigate what is the best final solution before even making the first prototype. And though it allows to have faster, easier, and safer development, so you can drive your virtual prototype very early in the development process, and then at the end build your vehicle with very few iterations or in a faster time. So to achieve this, we have developed at ViaGrade what we call a unique architecture. So why do we spend so much time developing this kind of architecture from others that can exist on the market? So driving simulators are, as I said, nowadays a new automotive development platform that allows designers, engineers, drivers from both OEMs and suppliers to work together in a safe environment and to test, develop, design in co-simulation environment place. But to be efficient, a driving simulator must deliver perfect immersion and very realistic motion feedback to the driver in order to accurately evaluate new design. A driving simulator is a driver-centered machine where the driver is supposed to really evaluate and test new solutions in a very, very accurate way. ViaGrade has developed a unique motion platform architecture called the driver in motion, the DIM, that allows us to do several, let's say, critical points. The first one is drive naturally. It can sound maybe, I would say, simple idea, but in a driving simulator, as we have limited workspace and limited feedbacks, we need the driver to drive as naturally as possible to evaluate our design, our solution, the same way, exact same way that he would have done in the real life. Otherwise, if he adapts, if he changes the way of driving, the way he tests it will change, and of course, the conclusion will change also. We wanted also to maximize feedback thanks to independent or redundant degree of freedom. I will detail this further on. Have an efficient workspace usage because having a big workspace is not always a solution if you don't use it properly. Some systems have a very big workspace, but as you do combined maneuvers, the workspace is drastically reduced because the machine cannot use properly all the space he has. So it's a really important point to develop. And finally, have quick and fast reactions thanks to stiff and sharp motion platform. If you have a very big workspace and a big machine, but that cannot sustain big accelerations or fast movement, okay, you can have a slow, but you can never cover all the spectrum of reactions. So those are the key points we focused on developing our unique architecture. And by developing this kind of architecture, we are bridging the gap between testing and simulation because we can allow to have multidisciplinary approach. That is, all the automotive disciplines can be covered by one machine. So this is what I will show you at the end of this presentation. So a little video to illustrate you our unique architecture for unparent separation of chassis and body behavior. What you can see here, we could see here was the DIM. So they are based on a unique concept with 9 degrees of freedom, with a combination of a lower and an upper stage to exploit at the best the workspace. So here you can see you have 6 degrees of freedom on the upper part and 3 degrees of freedom on the lower part. So the lower stage is built for chassis dynamics because you have a low dynamics movement possible with this, and it's X, Y, and yaw driven up to 5 Hertz. So you can see here on this little video, it gives feedback of lateral acceleration and longitudinal acceleration for both on gas or on brake feeling, and is really dedicated to low dynamic maneuver. The upper stage is dedicated for body dynamics. So it has 6 degrees of freedom and have a response up to 50 Hertz. So very sharp, very quick reactions, and particularly suited for ride and comfort studies, as you can see on this video, where you will drive on bumps or irregularity on the roads. You can see that the hexapod fast response will react quickly. So this is the main ideas behind our unique architecture that I will now just detail a little bit more. So if we come back on the architecture you just saw, as I said, with the lower stage called the tripod, we can really low frequencies and tire to road contact with 3 degrees of freedom for vehicle dynamics. The upper part, as I explained, is an hexapod with 6 degrees of freedom, so for typically high frequencies. So what we can understand from this concept are, let's say, 2 main ideas. The first one is that you have a separation between low and high frequencies. So it allows every stage of the simulator, the lower or the upper stage, to give every time the best frequency response and best frequency coverage in every situation, because you have no overlap and one device is not responsible of delivering all the frequency range. Also, as you can see, we have 3 degrees of freedoms on the tripod lower stage and 6 on the upper stage. So we have redundancy of degrees of freedom, so especially for X, Y, and yaw. It allows to have a separation between a quick reaction of the upper stage that will give you very quick kicks on very high dynamics maneuver for the X, Y, and yaw, and then the temporal feeling of the acceleration with the lower stage that will give you the temporal and the, let's say, the feeling of the temporal acceleration for the same degrees of freedom without saturating the hexapod. So by combining this hybrid and unique architecture, we can have a very efficient usage of our workspace because we do not saturate the machine, and we have also always the best response in every situation. To illustrate that, a very short video showing you the DIM 150. So 150 stands for 1.5 meters of workspace available both in X and Y, doing a quick lane change, maneuver. So as you can see on this video is that we clearly see how the upper stage quickly reacts and kicks very quickly for the maneuver, and how the lower stage comes afterwards and start moving, let's say, after the upper stage, but give you more the temporal effect of the acceleration, while the upper stage is coming back in place and ready to give you the next kick for the next maneuver. So you can see you can have quite high amplitudes and very, very sharp reaction, quick reaction, as I said, so you can use properly your workspace, and you have also a great reaction capabilities. So that is for, let's say, our unique architecture. And now to raise the bar again, ViaGrade has come up with a new simulator, a new concept that use exactly the same philosophy, exactly the same principles we just detailed, but with a different technology. So here is our brand new simulator called the DIM 400 for 4 meters of workspace that is cable driven, as I will detail in a few seconds. So I have also exactly the same philosophy with a separation and a two-stage machine, but a technology that allows you to have a bigger workspace with still high reactions. So, an extended workspace, what are motivation? Why, from what I show you with the DIM that are available in 150, 250, that means 1.5 and 2.5 meter size, why did we develop a new extended workspace machine? The challenges are very related to some specific, let's say, disciplines. As I said, a simulator has a limited workspace. And so by limiting this workspace, you limit the feeling, acceleration feeling, and the temporal acceleration feeling. This can be especially a problem for low dynamic maneuver, like slow ADAS maneuvers, lane change, have the good brake feeling, have road scenarios with long humps, compression, or big curves, and also when you put non-experienced drivers in a driving simulator. I don't know if you ever tried a driving simulator, but generally speaking, on a simulator that has very low feedbacks, you tend to go too quick or to have a driving that is not the one you would have in a real car. Because of what? Because you do not sense the danger, you do not sense the accelerations or the movement that in a real car would tell you, oh, I'm too fast, or I'm braking too hard, or I'm taking this curve far too fast. So by increasing this workspace, we can give the drivers, all the kind of drivers, not only race, motorsport, or test drivers, but also drivers that, let's say, normal users that will be able to judge if our ADAS or autonomous vehicle is safe, the good feelings and the good feedbacks. So the solution we have developed is to increase lateral and longitudinal maximum displacements from plus or minus 2 meters, so 4 meters overall. We have increased the yaw angle maximum rotation, and still we have exactly the same philosophy with, for example, a low stage with X, Y, and yaw, the disc frame, that are independent from the have also this 6 degrees of freedom, and also higher Z capabilities for, as I said, for example, with roads with long humps or compressions. So these new systems allowed us, with exactly the same philosophy, to even more separate the different contribution and to increase the amplitude of the different degrees of freedom. So the benefits are a smoother motion washout. So the washout is when the simulator will come back in position to prepare the next maneuver. This motion can be sometimes can provoke sometimes motion sickness. So if you increase the workspace, you have less needs. You can see on this image that the simulator is not always trying to come back at the center of the platform, and it can sustain very long acceleration or long period of time and still giving you a good feedback. So it results in a reduction of simulator sickness and a better feeling, a better feedback feeling. So this is the right solution for all OEMs because you have exactly the same capabilities and the previous simulators with extended workspace. Of course, all tire manufacturers and tier 1 suppliers, because if you want a very high amplitude maneuvers, lane change, and really better acceleration feeling, this is the best machine. And also, due to the fact that it has exactly the same response capabilities and stiffness and accuracy and let's say acceleration capabilities, it also suits high-end motorsports applications. So if we just have a look about the system itself, so previously you saw that we had a lower platform with 3 big actuators and an upper platform that is an hexapod with 6 actuators. Here we have 4 + 9 actuators driving simulator. So we have, of course, the base frame. Then we have the disc frame that is, so we can see here, the disc frame that is the lower part, so here, where the cables are attached for low frequency motion with 3 degrees of freedom. Then you have what we call the hexalift instead of an hexapod that is here for the 6 degrees of freedom and high frequency motion. And finally, below you have what we call the ICS that is here to compensate inertia and the vibration from the upper stage. So a little video to show you the DIM 400 that is in situation here of a replay on the Portimao racetrack. So what you can see, what is the striking difference? You can see the yaw capabilities are incredible due to the cable system. Basically, the cable can have less limitations than the actuators. If you have an actuators from a certain length, once you are at the limit of the actuator, you cannot do yaw or lateral dynamics anymore. Here, due to the cable system, you can still have a lot of yaw and still, while you are doing a very big amount of yaw, having a big lateral displacement at the same time. So you have a really more capabilities, especially in combined acceleration and yaw than the previous system due to the cable system and the extended workspace. And also, you can see that the upper platform, the Z capabilities can be very, very high. Because of the even better decoupling between the different degrees of freedom, we have increased the Z capabilities, vertical capabilities of the system. So this simulator is the new piece in our simulator strategy at VIA Grade, where we cover all the different scales from a desktop static simulator for first approach debugging and development, to then our compact static simulator or full-scale static, and then our dynamic lineup from small to full-size dynamic with a scalable concept like the cable simulator. To finish on that, I wanted to talk to you about the multidisciplinary approach that I introduced in the first slide. So, as you have seen, with all the different capabilities of this system, like the stiffness, the frequency response, and the redundancy and separation between high frequency and low frequency, it gives the possibility to have all the different kind of automotive disciplines with one machine. If you want to do ride and handling, you have enough frequency response to give you all the bumps, all the road contact feeling that you need. If you want to do NVH, we have also with our sister company HBK develop all the technology for vibration, high frequency vibration that you can use in our driving simulators. For ADAS and autonomous vehicles, as I explained, with higher workspace, you can experience really what you would experience in a car on low dynamic maneuvers on the road, on the open road, on a roundabout, on the highway, in a city, and experience really the good feeling in a car to evaluate if your ADAS or your autonomous vehicle algorithm is reacting properly. Of course, HMI, because as you have seen on some videos, we can put a real car cockpit on the car. So you are driving your car with the real car interface. And as we said also, of course, high-end motorsport usage with faster dynamic, high dynamic capabilities of the system. So as conclusions, ViaGrade DIM architecture allows unparalleled separation of chassis and body behavior, as I have showed you. It is bridging the gap between testing and simulation by providing the most immersive and driver-oriented motion system architecture, allowing to cover all development area. So on the right, you can see our latest DIM videos that you can also find on our YouTube channel, showing, for example, here our DIM around Idiadar track. If you are more interested in going in further detail about our DIM technology or simulator technology, you can visit our website. Also, our YouTube channel presents a lot of different videos about our technology, about conferences, our webinars, and so on. Our LinkedIn page, you will find all our latest news and our latest announcements. And of course, you can contact me directly if you have any questions or you need any more info about our technologies. We will now move to the Q&A. At the end of the Q&A, I will put a link in the chat with a little survey. So it's just a very short survey to ask you if you liked our webinars, how is your opinion about our webinars, if you want to have it improved, if you have any suggestion, we will be glad to hear it. Thank you very much for your attention.
Okay, so a few questions coming in. So bear with me 1 second, and I will share my screen. Okay. So hopefully you see the slides now. The first question, what workspace sizes are available for the various dynamic simulators?
Okay, so as I said, we have at the moment 3 dynamic simulators with 3 different sizes. The DIM 150, the DIM 250, and the DIM 400. So it means 1.5, 2.5, and 4 meters size workspace. So full size, that is plus minus divided by 2. So full workspace, 4 meters, 1.5 meters, 2.5 meters, X and Y.
Okay. Then the next question is, what is the maximum frequency that can be generated on the DIM 400?
On the DIM 400, it's very similar to what I explained to the with the DIM 150 and 250. So we have between, let's say, very low frequency, 0.5 to up to 30, 40 hertz, 50 hertz frequencies. The platform only. And then we can also have, as I explained, for NVH and ride and comfort application, we can go higher with our shaker system that can go up to, let's say, 250 hertz. So a combination between our platform and our shaker system, you can cover from 0 to 250 hertz frequencies.
Okay, and then finally, how much G-force can the driver feel on the DIM 400?
So, sorry, yes, Mark.
I suppose they mean like peak G-forces.
Okay, yeah. So on the G-force you can feel on the X and the Y are 1.5 G, and on the Z are 2.5 G.